Hello students, welcome back. This is part 2 of our series on basic matrix operations using Sage. In the first part I created about a 6.5 minute video on getting us to this point where we can solve a system of equations. So we were able to define a matrix, the right hand side, and then solve this system. Now I'm going to move on to, you can also solve it by setting up an augmented matrix. And so remember that A is a method, so it's going to be A dot augment B, and we're going to define that as a new matrix B, and if I hit Shift Enter, I get this augmented matrix. And then of course if you do row reduced echelon form, that's RREF of this matrix, you'll get the identity matrix and you get the right hand side, which is the solution. Notice that's 15 over 7, 9 over 7, 141 over 7. That was the solution we got when we solve this system of equations. That's another way to go about this. And sometimes you want to see the matrix and the augmented matrix in row reduced echelon form, especially if you have like underdetermined or overdetermined systems and you want to look at the rank of a matrix. There's lots of interesting properties for doing that. Not necessarily the way that, like if you just want to solve a system, you'd probably do something like the solve right or the backslash operator. But I just thought it'd be something that'd be fun to take a look at and might pique some curiosity for you. Okay, now one more thing I want to say here is you'll notice that these methods have parentheses after them. For those of you that are not aware of this, all methods need a parentheses after them. If you just typed in RRE, let's say F, it did an autocomplete there. So if I did RR and then hit tab, they would autocomplete for me. If I just hit Shift Enter here, it would say, oh, that's a built-in method, RREF of Sage. Okay, and it gives me the memory address where that's at. In order to get the method to activate, I need the parentheses, and there it is again. Okay, I'll just leave that there. Now, here we want to compute the right eigenvectors, RIGT. So this is A lambda equals lambda V. I'm sorry, AV equals lambda V. I apologize. AV equals lambda V. That's what the right means. So the eigenvectors on the right. There are left eigenvectors as well, which are VA equals lambda V. But this you may not find quite as useful as the next thing when we get to eigenmatrix. But I did want to point out a few things here. This is capital V. If I put in V of 0, that is the first eigenvalue and eigenvector. If I put in, and this is Python indexing, so this is going to be starting from 0. If I put in 1, I will get the next eigenvector. And the little 1 down here is telling me what the multiplicity is. So this is the eigenvalue 1 with eigenvector 0, 0, 1. And then if I put in 2, I get the eigenvalues minus 1 with this eigenvector, and that is multiplicity 1. That's what that's telling me. So those are my corresponding eigenvalues and eigenvectors. And it's not telling me it's a tuple. So let me just see this for a moment. There we go. So that would get me the minus 1. And then if I put in, if I get the indexing right, there we go, that's my eigenvector. So 0, so V2, so it's 0 for the first eigenvector, 1 for the second eigenvector, and 2 for the third eigenvector because our indexing starts at 0. V2 gives me this component of it. I'm sorry, V2, 1. So this is V2, all of V2. So let me just show you again what V2 is. Maybe that's a little confusing. There you go. Now, the 0th component of V2 is minus 1. That's the eigenvalue. If I put in 1, that should give me the eigenvector. And then if I put in 2, that'll tell me the multiplicity. Okay. So if you wanted to access the eigenvector, for example, you would do something like that. And if you want the second eigenvector or the first eigenvector, you would do those corresponding things. Now, what I'm going to do here is I get two outputs when I compute eigenmatrix right with the parentheses. And I encourage you to examine what eigenmatrix left would do. The outputs are going to be D, comma, and P. Now D is going to be a diagonal matrix of with the eigenvalues, and P is going to be the matrix of eigenvectors where the columns are the eigenvectors. And these should look familiar to you, right? Here's V0, 1, 2, 1. Here comes V1, which is 0, 0, 1, and that's the next column. And again, here is the third eigenvector, V2, which is 1 minus 2/3, 1. All right, and then here is the inverse of the eigenvector matrix. And you might remember that you can decompose a matrix A that is diagonalizable by multiplying P times D times P inverse, and we would get A back again. So if I do this right, that should equal A, and that is true. And notice the double equal sign for single equals in computer language is assignment, double equals is a comparison. Okay, and then if I go the opposite direction, if I go P inverse times A times P, I get the matrix D again, D, which is the diagonal matrix, which is 7, 1, minus 1 on the diagonals, and that gives me on the diagonals are the eigenvalues. Now, P, like this, P with a colon, this is called a slice operator. That gives me the first column. The slice means give me all of the row numbers, and 0 is the first column of the matrix, P. So let me put P up here for you so you can see that. So there's column 1. If I did it the other way, if I went all the columns and I hit a 0, I would get the top row. But let's do all the rows, and let's do the middle column, 0, 0, 1. And let's do the last column, 1 minus 2/3. So that's called that colon, that's called a slice. And then of course, if I take A times the first column, I get 7, 14 minus 7. Now if we look at that, let me go back to 0 here. That is 7 times this column. Well, that makes sense because that should be 7 times, that's AV equals lambda V. And lambda V, lambda is 7 in this case, and that's the eigenvalue. So that's just confirming that. All right. I'm going to stop here. I do some other fun things with quadratic forms and stuff. I'll just leave that at the bottom if you wanted to explore this sheet. Right now, I think we've gotten enough to be dangerous, and we've met all the functions for our needs for now. So I'll stop here, and I'll wish you luck.